Good evening. Welcome back, students. So, as promised, I have brought this second lecture on the screw gauge portion. As you can see, we have a screw gauge over here in a box, and we also have a wire. Okay, you can see. I'll just show you this. This is a wire, a very thin wire that we have. Okay, this is that wire, and we will measure the diameter of this particular wire. So naturally, the reason why we are using a screw gauge is, as I told you earlier also, that just like a vernier caliper and a normal scale, this screw gauge also is used to measure lengths, but these lengths are not the lengths that we usually can see with the help of our eyes very clearly, and these lengths are not big lengths or large lengths. Okay, these are extremely thin of you can for example see this particular wire. Okay, now the diameter of this wire is going to be very small because this is a very thin wire. Okay, if you want to use a normal scale to measure the diameter of this wire, you will certainly not be able to measure it accurately, because it is very obvious that one marking on the main scale is going to be more than the diameter of this particular wire. So let's say, for example, if I show you a normal scale also, let's say for example this is that scale, and if I show you, let me just zoom this a bit. Supposing that you have this. Okay, now you can see that the diameter of the wire. Now you see I have kept this particular wire. Let me just hold this wire. Okay, now have a look here. Let's say if I take this 8th reading and 8.1 reading. Okay, now this naturally you know that this is 8 centimeter mark, this big mark. Okay, it is written also 8, and this next mark is 8.1. Okay, so now you see, if we want to measure the diameter of this particular wire, you can naturally see when I'm keeping it at the 8 centimeter mark, you can see that the whole body of the wire in terms of the diameter is not enough to fill this gap of 8 and 8.1. So it's like this is even lesser than 1 millimeter. Okay, the diameter of this wire is even lesser than 1 millimeter. So certainly you cannot use this scale, because this scale can measure only a minimum value or a least value, as we use the word least count, of 1 millimeter. Okay, it cannot measure anything less than 1 millimeter, and naturally this wire is having a diameter of less than 1 millimeter, because it is not even overlapping a single space between any two markings. Okay, so that is the reason why we need a different instrument, and therefore this instrument comes into play, which is the screw gauge. So as usual, we will first go through the different parts of this particular setup. Okay, so let me just take this out from the box. You have this as the screw gauge. Let me bring the diagram in front of you first. So it is this diagram that I am talking about. Okay, so this is the screw gauge, as you can see in the books. This is the ratchet portion. So this ratchet portion is actually used to move the screw forward and backward. Okay, so you can give it a clockwise movement also, so that it moves forward, and then you can give it an anti-clockwise movement also, so that it comes backwards, just like a normal screw functions. Okay, so that is exactly the reason why the principle of a screw gauge, the principle of working of a screw gauge, is exactly the same as the principle of working of a screw. Okay, if you rotate the screw head clockwise, it moves forward, and if you rotate it anti-clockwise, it moves backwards. Okay, so that is the principle of working of a screw gauge. Now this U-shaped solid portion that you see, it is the U-shaped frame, which actually holds this particular screw with the spindle in front, and this is the stud. So let me just show you this over here. You can see these two portions. Okay, this particular portion, it has come out because I have actually given the clockwise rotations to the ratchet, so it has moved forward, and you can also see this U-shaped frame is there. Okay, and naturally this is the circular scale that we will see. It is incorporated in this hollow cylindrical portion that we have. So where is that cylindrical portion? It is this cylindrical portion that we have, and you can naturally see all these readings, they are circular scale readings. Okay, now Hidden inside, you can see there is a base scale also. You see, this is also being called as the main scale or the base scale. Okay, and this is the baseline or the reference line. You can see this horizontal line, children, which is going this horizontal line. So let me just zoom this a bit. Yes, this horizontal line is what I'm talking about. So this is known as the baseline. Okay, so this scale on top of which this circular scale moves forward and backward, this main scale is exactly similar to our normal scale. Okay, so this is one of the you can say that even in case of a screw gauge, you have two scales. One is the main scale and the other one is the circular scale. The circular scale is also known as the head scale. Okay, so these two things, the stud over here and the spindle over here, they act as the jaws. Okay, so whatever you have to measure, you have to put it in between these two jaws and tighten it up. Okay, so that's the rough idea. Now let's come back to our exact instrument that we have. So now let me just show you the ratchet movement. Okay, so when now I'm rotating it anti-clockwise. Okay, so let's just have a look here. Now when I rotate this anti-clockwise, you can see that as and when I'm giving rotations to this particular circular scale, now this is the circular scale which keeps rotating back, and therefore it is moving out also. So as and when I keep moving it anti-clockwise, you can see if you can see this scale which is there, this is that base scale or the main scale that I was showing you in the diagram. So let me just zoom this a bit. Yes, I'm talking about this scale that is visible, that is now becoming visible because this circular scale is moving away. You see, I am giving this anti-clockwise rotation. You see, anti-clockwise. The more I give rotations, the more rotations I give, you can see that more and more part of this scale is coming visible. Okay, so it's becoming visible. Till now only 0 and 5 were visible. Now you can see 10 is also going to come up. See, this 10 also comes up, and similarly you can have a 15 also. So these are gaps of 5 each. Okay, so these are 5. So how much is the space between these two successive markings? Each successive marking is at a space of 1 millimeter each. Okay, please remember, children, that each of these markings, these are of 1 mm each. Let me show you this with the help of a scale also, so that you do not get confused. You can have a look here. Let me bring this exact 5 over here, so you will be able to see. See, children, this is the 5 centimeter on the normal scale, the Apsara scale that you can see. It is coinciding exactly with the 5 on the baseline, and you can see that all the other markings, they are exactly coinciding. So each of these markings are 1 mm each. Okay, so when somebody tells you what is the reading here, you will say 5 mm, 10 mm, 15 mm, and so on. Okay, so this portion, this line, this becomes the main scale or the base line. This horizontal line, if you see, this is known as the base line, and naturally this is the other scale is in the form of that cylindrical kind of a structure, and it has markings. Let me just show you these markings. They are starting from here. They are starting from 0, 10, 20, 30, 40, 50, 60, 70, 80, 90, and then back to 0. So that essentially means that this circular scale has 100 divisions. Okay, total 100 divisions are there on the circular scale. You can have lesser number of divisions also, 50 also. You can have more than that, 500 also, depending upon how precise and how how less a least count you want for this particular screw gauge. Okay, so as of now, the screw gauge that I have in my hand, let me zoom that back again. So this screw gauge that I have in my hand, it has one main line or the main scale, one circular scale having 100 divisions overall. This is that ratchet that I was talking about. So now let me move this ratchet in the clockwise fashion. Now I'm moving it ulta, so that is clockwise. Okay, so you can see that now the circular scale along with moving in a circular fashion, it is moving forward also, and it is pushing this spindle forward. Okay, so you can see over here. Let me zoom that a bit more. Yes, so now you will be able to see that this spindle is moving forward, and there will be a time when this spindle will actually come in contact with this. Okay, so in order to check for the zero error, because just like vernier caliper, you may have zero error in this also. Remember, in vernier caliper, when the two jaws were brought together, what did you check? You checked whether the zero of the main scale and the zero of the vernier, they were in line. Now here there is no vernier scale. Here instead of the vernier scale, you have the circular scale. Okay, so here in screw gauge also you have two scales. One is the main scale and one is the circular scale. So what do you have to see? You have to bring the two jaws together. So let me just bring these two jaws together, and we will see when they, yeah. So now the two jaws are together. Don't force this clockwise movement too much, so that the wire which is inserted in between later on, that may get deformed also. So just by rotating it, when you feel that there is no further movement possible, because they have all both of them come together, so now you will see. Let me just show you how you check for the zero error. You see, children, over here, let me use a pen to tell you this. You see, when the two jaws were not together, let me go back again slightly. Now you see, this particular horizontal line that you are seeing, this is known as the baseline. Okay, this line and the zero of the circular scale, if they come exactly in the same horizontal line, so that is like they have to match. So when do they have to match? When these two jaws have been brought together. Okay, so you can still see there is a gap in between. I have deliberately made the gap to show you this baseline. So now when I put it back again, let those two, you see this is spacing I am reducing so that they come together. So let's say when they come together, now this is the situation. Now see, children, this is the zero of the main of the circular scale, and this line here, have a look, this line here is the baseline. There is a small difference between them. You see, ideally this zero of the circular scale should have come somewhere here, so that they would have been exactly in line. But since they are not in line, had they been in line, then this instrument would have been free of zero error. But since the zero of the circular scale is above the zero of the baseline, so it has a negative zero error. Okay, similarly you can have a situation in which the zero stops somewhere below the baseline, somewhere here. Okay, so in that case it would have been a positive zero error. Nevertheless, we will assume that it does not have a zero error, so the no zero error situation would be something like this. This would be the baseline, and in the same horizontal line you would get the zero of the circular also. Okay, so this would be the situation, ideal situation, in which the screw gauge does not have any zero error. Now if that is the situation, now I'll tell you how to record the pitch and the least count of this particular screw gauge, and then we will know how to insert the wire in between these two studs and then get the reading also. Okay, so let us go back to the understanding of the pitch. Okay, so the next thing will be pitch of a screw gauge. Now this is something new, pitch of a screw gauge. Okay, please remember, children, this is gauge, G-A-U-G-E. Pitch of a screw gauge is the number of, or you can say in terms of the distance also you can write, this is pitch of a screw gauge is the distance moved by the circular scale linearly on the base line or on the main scale scale. Now let's first read it properly and then I'll show you what this means. Pitch of a screw gauge is the distance moved by the circular scale linearly. So linearly means like this, horizontally. Okay. Naturally, when I move the ratchet, what happens? The cylindrical portion goes round and round, and it moves forward also. When it moves forward, it actually moves linearly on the main scale also. So that distance in one complete rotation. So distance moved by the circular scale linearly on the baseline or on the main scale in one full rotation, of the screw. Okay, so now let us see what this means. Understanding this line may itself on its own may be a little complex, but when you have a look at this particular figure, actually you will understand it more better. So let's see what it means. Now let me just go back and hold my reading here. Now please have a look very carefully, children. What I want to show you is the calculation of pitch. Now you see this 30 mark. Okay, this 30 mark, you can see 30 here. This 30 mark is right now coinciding with the baseline. Okay, this is the baseline. Okay, this is the baseline. So this 30 mark is there exactly on the baseline. Okay, coinciding with the baseline. Now when somebody says one full rotation, that means this 30 should actually go back round and come back again here. Okay, so what will happen when I give this a complete rotation? Do you think that it will still remain, this reading will still, the cylinder end will remain at 5.1 here? Let's say for example, let me see the reading here. Right now it is 0, 1, 2, 3, 4, 5 and then 6th reading. So this is 6 mm. Okay, right now I can see 6 mm on the main scale. This is my main scale. You can see this 5 reading and this is the 6th reading. Okay, this is exactly on the border, that is why you are not able to see it clearly. So this is that 6 millimeter mark. Now this is that 30 on the circular scale. Let me give it a full rotation and you keenly observe, children, that this circular scale will move forward. So right now it is at 6th mark. How much does it move forward? We will have to see in one full rotation. So let us see. Let me get this a little more clearer first. So let's say for example we have okay, so let me see if I can show you that more clearly. Okay, now you see this 30 I'm going to move one full rotation. So you see here comes 30. Okay, so this 30, you can see, children, this 30 has again come back after one full rotation. It has come back. So I have given one full rotation to this, and now I cannot see the 6th reading. You can see right now it is at the 5th reading or the 5 mm reading. So that means earlier I was able to see till 6 mm. Now after giving one full rotation, I can see only 5 mm. That means how much has been the linear movement? 1 mm. Okay, so now let us go back to that definition. You see, distance moved by the circular scale linearly on the baseline or on the main scale in one full rotation. So when I gave that one full rotation, I started from 30, came back again at 30. You can start from 0, come back again at 0. How much linear movement has been done? Linear movement that has been done is 6 mm minus 5 mm. So that is, let me just show you here. So that is 6 minus 5. So that is 1 mm. Okay, or you can write this as 0.1 centimeter also. Remember, this is not the least count. This is the pitch of the screw gauge. Okay, now least count is very easy to calculate. It is going to be pitch upon total number of circular scale divisions. And remember, I told you how many total circular scale divisions are there on this screw gauge? 100. Let us see again. You can see yes, this is 0 and 10, 20. Okay, so let's go back again. You have 0, 10, 20, 30, 40, 50, 60, 70, 80, 90 and back to 0. So that means 100 total divisions are there. So we have calculated the pitch. So now let me show you. Pitch value is 0.1 centimeter. So 0.1 centimeter divided by 100, because there are total 100 divisions. So that becomes 0.001 centimeters. Okay, so the decimal will shift 2 places back because we have division by 100. So this becomes the least count of the screw gauge. Remember children, when we were discussing the vernier caliper has had 0.01 centimeter as the least count. So you can see that now we have the third place of decimal also. So this is even more precise and accurate. Okay, so now we'll go back to our process of determination of how we measure the diameter of that wire that we had seen. Okay, so the formula here will be diameter of wire is equal to, it may not be a wire, it may be some other thin kind of an object. Okay, remember it has to be thin because we are using a screw gauge, so that has to what we are measuring has to be according to the device that we are using for measurement. Okay, so if there is something thick, we can use our normal scale or the vernier scale. Okay, so we have diameter as the main scale reading. Okay, just like we had in vernier scale, we had main scale reading. So this will be taken naturally from the main scale, which is hidden in the in that cylindrical portion on the horizontal line. Okay, so MSR plus N into least count. So the formula as such is essentially the same we were using in vernier caliper. The only difference here is that this time when we say N, it will not be the number of division of the vernier coinciding with the main scale, whereas here actually it will be number of division on the circular scale which is coinciding with the baseline. Okay, so let me write these down. Least count value we have already understood. This is 0.001 centimeter. So this will remain the same for our instrument. N, naturally it means division on the circular scale which is coinciding with baseline. So baseline, remember, is that horizontal line that we have, and MSR is naturally the reading that you can see on the baseline. Okay, so reading on the baseline. Okay, so let me just show you all these three things and then we will record the readings also. So now we will take up our thin piece of wire that we have along with the screw gauge, and we will insert this particular wire, thin wire, in between the screw gauge. So in between the stud and the spindle of the screw gauge. So let's say that this is the situation. Okay, so now I'll just zoom it back so that you can see. See children, when I have put this particular wire in between the two studs, you can see, let me just okay, so this is the situation here. You can only see the 0 on the main scale. Okay, only 0 can be seen on the main scale. See, only 0. Okay, so that would mean what? What is the reading on the main scale, or what is MSR? MSR is 0 mm. Okay, had it been at the first mark, had the first mark been visible, I would have written 1 mm, but this is 0 mm because only the first bar is visible. So let me go back to the formula. This is my formula. So in place of this MSR, I am going to now write down 0 mm. So in terms of centimeter also 0 mm is 0 centimeter plus. Okay, now you understand children why this is the diameter of the wire is lesser than 1 mm, but it is certainly more than 0. It cannot be 0, it has to be some finite value. Okay, now n, what is n? Division on the circular scale which is coinciding with the baseline. Now let's have a look back again. So let me just put this back again so that you can see. Okay, now this is the situation. So let me just zoom this a bit. Now let me see, what I wanted to show you here is this. Yes, you see children, this is the 50th division, but it is not coinciding. It has to coincide with the baseline. This is that baseline, the horizontal line. You see, this horizontal line is the baseline. So let us read. It will be slightly difficult, but we'll have to see. This is the 50th division, this is 51st, this is 52nd. I think 52nd division is coinciding exactly horizontally with the baseline. So you have to tally it with the baseline. This is the baseline. Okay, you can't simply say 50, because 50 you can see it is slightly below the baseline. Okay, so you have to look very, very carefully. So it is 51st, 51st, 52nd division. Yes, 52nd division is coinciding. So now let's go back to the formula. The formula says n, so n becomes 52 multiplied by least count naturally is known to us 0.001 centimeter. So this becomes 0 centimeter plus, now when this multiplies here you will get 0.052 centimeter. Okay, now when you add this up you will get 0.052 centimeter as the diameter of that particular wire, or you can write this as 0.52 mm also. So you see, this is almost half mm. Okay, that is exactly the reason, if you remember in the beginning of this particular video when I had tried to explain why you cannot use a normal scale to measure the diameter of this wire, I had shown you this, children. If you remember, I had shown you this. I had kept the wire in between any two readings here, and I had shown you that let me just show you back again. See, the entire thickness of this wire is not sufficient to form 1 mm. Okay, that is why we come to understand that the diameter is less than 1 mm, and you can see that it is coming out to be 0.52 mm, which is roughly half mm. Okay, and precisely you can see there are 3 decimal digits that are there. So using the screw gauge you can measure up to 3 places of decimal in terms of centimeters. Okay, so that can give you the detailed exact diameter of this particular wire. You can smoothen it out with the help of your hand also. Okay, so I hope children that you have got a fair bit of an idea of how to use this particular instrument, which is the screw gauge. Okay, I hope this lecture will help you in performing your experiments at least. Okay, so this is both at 9th and 11th standards you do make use of this particular device in performing your experiments. Thank you children.